How do the diagonal relationship between elements like lithium and magnesium or barium or aluminium manifest in their chemical properties? Diagonal relationship occur due to similar ionic sizes and charge densities across the periodic tables. Second and third periods influenced by the diagonal effects. Lithium and magnesium share similarities. Both forms nitrides. Both form nitrides Li3N Mg3N2 due to a strong polarizing power, have comparable ionic radii. Lithium plus 76 pm, magnesium 2 plus 72 pm, and exhibits covalent character in compounds. Example: lithium chloride versus magnesium chloride, beryllium and aluminium also align, forming amphoteric oxides. Amphoteric oxide BeOal2O3 that reacts with acids and bases, and both have diagonal covalent tendencies. Example: beryllium chloride polymerize like AlCl3. This relationship arise from increasing effective nuclear charge and decreasing atomic size, impacting reactivity and compound stability across groups 1 to 2 and 2 to 13. What role does the Ellingham diagram play in the metallurgy of metal like iron and copper? Ellingham diagram plot the Gibbs free energy chains, del G of metal oxides formation against temperature, guiding metallurgical reduction processes. For iron, the diagram shows Fe2O3 reduction by carbon via carbon monoxide become feasible below 700 degrees Celsius, where del G turns negative, explaining blast furnace operation. For copper, Cu2O reduction occurs at lower temperatures around 400 degrees Celsius due to a less negative del G supporting smelting with minimal energy. This diagram help select reducing agents. Example: carbon, hydrogen, and optimize conditions, balancing thermodynamics, and kinetics to minimize energy use and emissions in industrial metal extraction. How does the trans effect influence the synthesis of coordination compounds? The trans effect, a kinetic phenomenon in square planar complexes, describe how certain ligands, chlorine, carbon monoxide, levelize the position trans to themselves, directing substitution in PDCl 4 to minus synthesize, adding chlorine minus first place it trans to another chlorine, weakening the trans PT ligands bonds due to pi backbonding or pi repulsion, facilitating ligands exchange. This allows control synthesis of cis or trans PTCl to NH3 to with applications in designing displating where trans levelization ensures the correct geometric isomers for anti-cancer activity, optimizing therapeutic efficiency. What is the role of coordination compounds in homogeneous catalysis? Coordination compounds are pivotal in homogeneous catalysis, where the metal complex operate in the same phase as reactants. Weakens on catalyzed RHCl PPH3 facilitates alkane hydrogenation by coordinating the alkene alkene and hydrogen undergoing oxidative addition and reductive elimination to form alkanes with turnover numbers exceeding uh, 10 to the power 4. Other examples include CO4 minus in hydro formulation adding CO and is to alkanes. Their turnability, ligand choice, and defined active sites enhance selectivity and efficiency, driving industrial processes like polyester synthesis. How does the lanthanide contraction affect the properties of their allows the lanthanide contraction reducing ionic radius from Ce 3 plus 1.034 angstrom to Lu 3 plus 0.848 angstrom. Influence allow properties by enhancing lattice compatibility with transition metals in NdFeB magnets, neodymiums, smaller size 0.995 angstrom fits iron lattice, strengthening magnetic alignment and increasing coercivity up to 1.2 T. Similarity, mismetal CELAPRND allows with iron improve hardness and corrosion resistance in flints. These size trends also reduce ductility, necessitating careful allows design for applications like aerospace components. What are the potential future application of actinide chemistry beyond nuclear energy? Example, uranium 235 Pu 239 reactors. Actinide chemistry holds promise in advanced fields. Uranium luminescence properties in U22 plus complexes could enhance optical sensors. Thorium based molten salt reactors offer safer thorium 232 fuel energy with less long lived wasty actinide organometallics. You thought to may catalyze novel organic reactions. GUE to 5A orbital availability. Medical applications like targeted alpha therapy with AC225 target cancer cells, while their unique redox chemistry, example plus 5 plus 6 estates, could inspire new materials, pending safety and regulatory advancement. What are alkali metals and where are they located? In the periodic table, alkali metals are a group of highly reactive metallic elements found in group 1 of the periodic table, comprising lithium, sodium, potassium, rubidium, cesium, and francium. Positioned on the far left side of the periodic table, excluding hydrogen. These elements share a single what are alkali metals? What are alkali metals and where are they located in the periodic table? Alkali metals are a group of highly reactive metallic elements found in group 1 of the periodic table, comprising lithium, sodium, potassium, rubidium, cesium, and francium. positioned on the far left side of the periodic table, excluding hydrogen. These elements share a single s electron in their outermost shell. Example: sodium Ne 3s1. This electron configuration makes them eager to lose that electron to a stable noble gas configuration, resulting in a +1 oxidation state and strong reducing properties. Their reactivity uh, escalates down the group due to a decrease in ionization energy caused by increasing atomic radius and reduced nuclear attraction, as seen in the violent reaction of cesium with water, producing cesium hydroxide and hydrogen gas. 2 cesium plus 2 S2O is equal to 2 cesium hydroxide plus hydrogen. What are alkaline earth metals and what makes them different from alkali metals? Alkaline earth metals located in group 2 include beryllium, magnesium, calcium, and strontium, barium, and radium. Unlike alkali metals with one valence electron, these elements have two electrons in their outermost s orbital. Example: magnesium neon 3s2, leading to a +2 oxidation states. This dual electron configuration requires more energy to remove both electrons, making them less reactive than alkali metals, but is still highly reactive compared to most elements. They form stable ionic compounds, calcium chloride, and show increasing reactivity down the group due to larger atomic size and lower ionization energy, though beryllium covalent tendencies set it apart. What elements are included in group 3A to 7A of the periodic table? Group 3A to 7A UPAC groups 13 to 17 encompasses a wide array of elements. Group 3A includes boron and aluminium, metalloids and metals. Group 4A has carbon and silicon, key non-metals and metalloids. Group 5A featured nitrogen and phosphorus, non-metals with varying allotropes. Group 6A contains oxygen and sulfur, essential non-metals. Group 7A, the halogens includes fluorine, chlorine, bromine, iodine, and astatine. Highly reactive non-metals. These elements properties range from semiconductive silicon to diatomic gases, nitrogen oxides, and corrosive liquids. Bromine 2, driven by 3 to 7 valence electrons and their position in the p blocks. Why are halogens highly reactive? Halogens in group 17 are highly reactive due to their electron configuration with 7 valence electrons. Example: chlorine neon 3s2 3p5, one short of a stable octet. This derives them to gain an electron to form one ions. Example: chlorine ions, or share electrons in covalent bonds. as in ACl. Their reactivity peaks with fluorine, the most electronegative elements, and decreases down the group of fluorine, chlorine, bromine, iodine, due to increasing atomic size, which reduce electron affinity and strengthens X bond. Example of fluorine is weaker than iodine due to lone pair repulsion. They reacts exothermically with metals. 2Na plus Cl2 is equal to 2NaCl and hydrogen. What is metallurgy and what is its purpose? Metallurgy is the scientific and technological discipline dedicated to extracting metals from their naturally occurring ores, minerals compounds like oxides or sulfides, and refining them into pure or elevate forms suitable for use. Its purpose is multi-faced. It involves processes like crushing, smelting, and electrolysis. To isolate metals, example iron from hematite. Assess their physical properties. Example ductility, conductivity, and optimize their applications in industries such as contraction, steels, electronics, copper, and aerospace, titanium. It also address environmental concerns like sludge disposal to ensure sustainable metals production. How is magnesium extracted from its ore? How is magnesium extracted from its ore? Magnesium is extracted from ores such as magnesite, MgCO3, or dolomite, CaMgCO3 2, through a detailed process. Initially, the ore is calcinate at high temperatures around 700 to 1000 degrees Celsius to decompose it into magnesium oxide and carbon dioxide. This magnesium oxide is then converted to magnesium chloride MgCl2 by chlorination with hydrochloric acid or reaction with ammonium chloride. The final step employs the Doi process where molten magnesium chloride is electrolyzed in a steel cell with a graphite anode and iron cathode. Reducing magnesium 2 plus is magnesium metal at the cathode, while chlorine gas evolve at the anode. The resulting magnesium is used in lightweight alloys for aircraft and automotive industries. What is the primary ore for aluminum and how is it processed? The primary ore for aluminum is bauxite, a complex mixture of aluminum oxide, Al2O3, X S2O, and impurities like iron oxide. Processing begins with the Bayer process. The bauxite is pulverized, mixed with sodium hydroxide under high pressure and temperature, 150 to 200 degrees Celsius, dissolving aluminum hydroxide into sodium aluminum. After filtration to remove impurities, the solution is cooled to precipitate pure alumina, Al2O3. This alumina is then refined via the Hall Herold process, an electrolytic method using a molten chrolite Na3Al F6 bath at 950 to 980 degree Celsius, where alumina dissociates and aluminium is reduced at the carbon cathode with oxygen reacting at the anode to form carbon dioxide, yielding high purity aluminium for packaging and construction. How is iron extracted from its ore? Iron is extracted from hematite Fe2O3 or magnetite Fe3O4 using a blast furnace. A towering structure operated continuously. The furnace is charged with ore, coke, carbon, and limestone CaCO3. Preheated air up to 1200 1200 degrees Celsius is blast in igniting coke to produce carbon monoxide and heat. Carbon monoxide reduced iron oxide to molten iron Fe, while limestone decomposes into calcium oxide CaO and carbon dioxide with calcium oxide forming a sludge. By reacting with silica impurities, molten iron settled at the bottom, tapped periodically, and is further proceed into steel by adding carbon or alloys, serving as the backbone of infrastructure and machinery. What is the common oxidation states of transition metals? Transition metals groups 3 to 12 exhibit multiple oxidation states due to the involvement of d electrons in bonding. For instance, iron Fe commonly shows plus 2 Fe2 plus, example FeCl2, and 3 plus 3 Fe3 plus, example Fe2O3. Copper displays plus 1 Cu2O and 2 plus and plus 2 CuSO4, and chromium ranges from plus 2 CrCl2 2 plus 2 Cr2 O3 2 plus 6 CrO 4 2 minus. This versatility arises because d orbitals can lose electrons or participate in hybridization, enabling diverse coordination of compounds and catalytic roles such as manganese has plus 7 state in KMnO4 used as an oxidant. What is aqueous chemistry in the context of transition metals? Aqueous chemistry of transition metals explores the behavior of their ions in water, they typically form hexa-aqua complexes, FeS2O6 2 plus or CuS2O6 2 plus due to water's lone pairs coordinating with the metal. This field examines solubility FeS2O6 3 plus hydrolysis to form acidic solution, redox reactions, example Fe2 plus to Fe3 plus with oxidants and ligands substitution, example NiS2O6 2 plus 6 NH3 is equal to NiNH3 6 2 plus 6 H2O, often accompanied by color changes. These properties are critical for understanding their roles in catalysis and analytical chemistry What are oxides and halides of transition metals? uh, what are oxides and halides of transition metal oxides formed by a reaction with oxygen include Fe2O3 rust plus 3 state, CrO3 plus 6 state, a strong oxidants, and Ti O2 plus 4 state, a white pigments. This very from ionic FeO two covalent CrO3 based on oxidation state and metal size. Halides resulting from halogen reactions include FeCl3 covalent plus 3 TiCl4 covalent plus 4 used in polymerization and CuCl ionic plus 1 their properties color magnetism and reactivity depends on the metals electronic structure making them valuable pigments catalyst and material science. What are lanthanides and where are they found in the periodic tables? Lanthanides are the 15 elements from cerium, jade, 58 to lutetium, jade, 71 positioned in the A block at the periodic table's bottom. Following lanthanum La, there are 4 f orbitals fill progressively. Examples Ce, Ze, 4f1, 5d1, 6s2, 2luxe, 4f14, 5d1, 6s2, leading to similar chemical properties due to lanthanide contraction found in minerals like monazite. They are critical for magnets, Nd, phosphorus, Eu, and laser and lasers, Yb. Despite their rarity and complex separation. How are lanthanides isolated? Lanthanides are isolated from bodies like monazites, phosphate minerals, or bastnasites, a fluorocarbonate through a multi-step process. The ore is digested with sulfuric or hydrochloric acid to form a soluble lanthanide salts, followed by precipitation to remove impurities, separation and release ion exchange chromatography, where lanthanide ion are differentially absorbed onto a resin on eluted with complexing agents, citrate or solvent extraction using organic solvent, exploiting slight ionic radius differences due to lanthanide contraction of water aqua ion and oxo salt in lanthanide chemistry. Aqua ions are hydrated lanthanide complexes such as Ce S2O8 3 plus or Gd S2O9 3 plus formed when lanthanide dissolved in water with coordination numbers 8 to 9, reflecting their large ion ready and high charge oxo salts like lanthanide oxalates Ln2C2 O4 3 or nitrates LNNO3 arise from reactions with oxo acids often as precipitates in purification. These compounds highlight lanthanides preference for oxygen donors and high coordination coordination influencing their use in catalyzed and optics, use in catalyzed and optics. What is a coordination compounds? A coordination compounds is a complex where a central metal ion or atom, example CO3 plus, CO3 plus, PT2 plus is surrounded by ligands, molecules or ions with lone pairs, NH3, Cl minus, H2O forming coordinate covalent bonds. Example include CO, NH3, 6 Cl3, where 6 NH3 ligands coordinate covalents, and the chlorine ions are counter ions. These compounds exhibit unique properties like magnetism, and stability, playing roles in catalysis weakens bonds, catalyzed medicine, cisplatin, and inorganic chemistry, hemoglobin, bioinorganic chemistry, hemoglobin. Who developed the nomenclature for coordination compounds, compounds? Alfred Weiner's, a Swiss chemist, pioneered the nomenclature and structural theory of coordination compounds, earning the 1913 Nobel Prize in chemistry. His groundbreaking work in the late 19th and early 20th centuries proposed that metals exhibit primary valency, oxidation state, and secondary valency coordination number, explaining complexes like CONH3, 6 Cl3. His insights into stereochemistry and isomerism laid the foundation for modern coordination chemistry. What is the Werner primary valency concept? Werner's primary valency concept defines the oxidation state of the central metal ion corresponding to the number of negative charge it valence in the coordination spheres, outer spheres, in CONH3, 6 Cl3 cobalt plus 3 oxidation states. Primary valency is balanced by three chlorine ions, reflecting ionic interactions. This valency determines the compound's overall charge and is distinct from coordination number, providing a framework for understanding ionic versus coordinate bondings. What is the secondary valency in coordination compounds? Secondary valency or coordination number is the number of ligands, donor atoms directly bonded to the central metal ions via coordinate bonds. For CONH3 for 2 plus, the secondary valency is 4 S4 nitrogen atoms from NH3 ligands coordinate with Cu2 plus, typically forming a square planar geometry. This valency dictates the complex shapes. Example octahedral for 6, tetrahedral for 4, and influence stability of an ranking from 2 to 12 depending on the metal and ligands. What is Sidgwick electronic concept? Sidgwick electronic concept developed by Neville. Sidgwick explains coordination of compounds forming through the donation of electrons pairs from ligands, lone pair to the metal ions, empty orbitals forming additive coordinate bonds for NiCO4 carbon monoxides. Lone pairs donates to nickel 3d and 4s orbitals, stabilizing the complex. These effective atomic number En roll where the metal acids A noble gas configuration complements a warmer structural model, enhancing understanding of bonding of reactivity, reactivity. What is a valency bond theory in coordination chemistry? Valency bond theory, VBT, proposed by Linus Pauling. Describe coordination compounds formation by the hybridization of metal orbitals with elegant orbitals in CONS3 6 3 plus CO3 3d6 uses inner 3d 4s and 4p orbitals to form D2 sp3 hybridization accommodating 6 ns3 ligands in an octahedral arrangements. This theory explains geometry and paramagnetism. Example: high spin versus low spin complexes. Though it's limited by its inability to predict spectral properties accurately, later defined by crystal field theory. What factors affect the stability of coordination compounds? Stability of coordination compounds depend on several factors. The metal ions charge and size, higher charge density. Example: CO 3 plus increases stability. Ligands, strands, strong field ligands like cyanide versus weak fields like S2O, and environmental conditions, pH, temperature. The silate affects using multidentate ligands like EDTA enhance stability by forming multiple rings, releasing entropy. Stability constant. Example: log K for efficiency 4 minus 24. Quantify this. Influencing applications in solution therapy and catalysis. What is isomerism in coordination compounds? Isomerism in coordination compounds occur when the same molecular formula yields different structures, geometries. Isomerism sees PTNS3 to Cl2 versus trans arises from ligand position differences. Optical isomerism CO EN3 3 plus enantiomers from a serality linkage. Isomerism example: CONS3 5 NO2 2 plus versus CONS3 5 ONO 2 plus from different ligands, attachments points, and ionization. Isomerism example: CONS3 NS3 5 ISO4 Br versus CONS3 5 Br ISO4 from interchangeable counterions. These variations impact properties like color and biological activities. How are coordination compounds used in a biological system? Coordination compounds are integral to biology. Homoglobins Fe2 plus center coordinates with O2 and histidine in a heme complex enabling oxygen transport in blood. Chlorophylls Mg2 plus is coordinated by a porphyrin rings for photosynthesis, converting light to energy. Vitamin B12 CO3 plus coordination facilitates methyl group transfers in metabolism. This bioinorganic rules highlight the importance of metal ligands metal ligands interactions in life processes with applications in mimicking these systems for drug designs. What are what are inert gases, and why are they called so? Why are they called so? Inert gases or noble gases group 18 helium, neon, argon, krypton, xenon, radon are called so because they are closest shell electron configurations. Example: neon 1s2 2s2 2p6 provide exceptional stability with fields s and p orbitals. These complete octet or duet for helium minimize their tendency to gain, lose, or share electrons, rendering them unreactive under standard conditions. Exceptions like xenon fluoride with Fe F2 under UV light occur due to xenon's larger size and polarizability, but their inertness suit uses like shielding gases. What are some applications of inert gases? Inert gases have specialized uses. Helium cools MRI magnets, and lifts balloons due to its low intensity. Neon glows in signs via electric discharge. Argon shields whales and fields in incidence valve preventing oxidation kryptons enhance laser laser precision. Xenon powers high intensity lamps and medical imaging. Xenon 133 133 and radon discovered radioactivity treats cancer via targeted radiation. Their non-reactivity ensures safety and efficiency in this applications. Why does xenon show some chemical reactivity? Xenon's reactivity rare among noble gases stems from its large atomic radius 216 pm and available 5d orbitals, allowing it to overcome its stable krypton 4d10 5s2 5p6 configuration under extreme condition. Example: electric discharge with F2. It forms compounds like xenon fluoride, ZeF2, XeF2, XeF4 and XeO3 by accepting electron pairs from a highly electronegative fluorine, or oxygen. This polarizability and electron accessibility distinguish it from a lighter, less reactive noble gases. What is the general trend in reactivity of alkali metals? The reactivity of alkali metals increases down group 1 lithium to cesium due to a decrease in ionization energy from 520 kilojoule per mole lithium to 376 kilojoule per mole cesium. As atomic size increases and nuclear nuclear shielding weakens nuclear shielding weakens the hold on the valence electron. This trend manifest in reactions with water. Lithium reacts slowly while cesium exploits producing MOAs and S2. Example 2K plus 2S2O is equal to 2 KOH plus S2. Lower melting points and higher electrode potentials down the group further enhance reactivity. How are chromium and nickel extracted? Nickel extracted. Chromium is extracted from chromite FeCr2O4 by roasting with sodium carbonate, Na2 CO3 and oxygen to form sodium chromate Na2CrO4, which is laced and reduced with aluminum in the aluminothermic process thermite reaction to produce pure chromium. Nickel is extracted from panthaladite, nickel iron 9 S8 by roasting to nickel oxide Ni O smelting with a matrix CuNi sulfide and electrolyte refining yielding nickel for stainless steel and battery electrode. What is the role of copper in metallurgy? Copper is extracted from chalcopyrite CuFeS2 through smelting to a copper matrix Cu2S followed by converting with air to blister copper and electrolytic refining to 99.9. What are the common oxides of lanthanides? Lanthanides form stable oxides due to their plus 3 oxidation states including CeO2 cerium oxide a catalyzed in auto exhaust systems Nd2O3 neodymium oxide a glass colorant and La2O3 lanthanum oxide used in optical lens. These are produced by igniting lanthanide metals or carbonates in oxygen exhibiting high melting points Nd2O3 at 220 2270 degrees Celsius and unique 4f electron properties making them available in ceramics and electronics. What are the coordination number in CuNS3 for 2 plus? The coordination number in CuNS3 for 2 plus is 4 ammonia NS3. 4 ammonia NS3 molecules act as monodentate ligands. Is donating a lone pair for nitrogen lone pair for nitrogen to CO2 plus. This typically results in a square planar geometry favored by D9 CU2 plus due to John Taylor distortion with bond longs around 2.0 angstrom. The deep blue color of the complex arises from DD transitions used in qualitative analysis for copper coppers. What is a silhouette effect in coordination chemistry? The Hillette effect is the enhance thermodynamics stability of coordination compounds with multi-denate ligands. Example: ethyl ethylene diamine or EDTA that form fillet rings with the metal ions for Ni En 2 plus 3 En ligands create five membered rings, releasing more water molecules, higher entropy than NS36 2 plus, increasing the stability constant. Log K is equal to 18 versus 8. This effect is crucial in sequestrating metal ions in medicine and industry. How do actinides differ from lanthanides? Actinides thorium Z90 to LR Z100 and 103 Z90 103 differ from lanthanides by their greater radioactivity. Uranium 238 Pu 239 decay, more variable oxidation states, plus 3 2 plus 6. Example: UO2 2 plus and 5F electrons that are more diffuse and available for bonding than 4F electrons located after actinium. They are synthetic beyond uranium used in a nuclear reactions, used in a nuclear reactors. UPU and opiums, contrasting with lanthanides, non-radioactive magnet. Relate applications. What is a geometric isomerism in coordination of compounds? Geometric isomerism occurs when ligands occupy different spatial spatial arrangements around the metal. Example: in PTNS3 to Cl2, the cis isomer has Cl ligands at 90-degree adjustment, while the trans has them at 180 opposites. This affect properties like dipole moments. Cis has one, trans does not, and biological activity displating is anti-cancer. Translating is inactive with geometries determined by coordination number and ligand size. What is the role of zinc in metallurgy? Zinc is extracted from sphalerite. Zinc is extracted from sphalerite zinc sulfide by roasting to zinc oxide. This reduced with carbon in a retort furnace or electrolyzed from zinc sulfide ZnSO4 solution. Its primary metallurgical role is galvanizing steel, forming a protective zinc layer 0.1 to 0.2 millimeter that corrodes preferentially extending steel life in construction. It's also allowed in brass CuZn and used in die casting for automotive parts. Why are transition metal oxides colored? Transition metal oxides are colored due to dd electron transitions in the metal, partially filled d orbitals split by ligands filled in a crystal field, or molecular orbital theory contrast for CuS2O6 2 plus D9 absorbed of red light 600 to 700 nanometer caused a blue appearance with extract color. Example: green for NiO, YOLO for CrO3, depending on oxidation state, ligand strengths, and geometry, making them useful as pigment and indicators. What is the oxidation state of iron in iron chloride? The oxidation states of iron in FeCl3 is plus 3 is chloride ion. Cl minus contribute a minus 1 charge, and with 3 Cl minus ion, the total anionic charge is minus 3. To balance this in the neutral compounds, neutral compound iron must be Fe3 plus consistent with its common plus 3 states in covalent ionic halides. This compound, a yellow solid, acts as a Lewis acid and catalyzes in organic synthesis. What is the significance of inert gases in lighting? Inert gases like neon emitting 600 to 700 nanometer red orange light, and argon with mercury vapor for 254 nanometer UV converted to visible light by phosphorus field fluorescence, and neon tubes when an electric current excited their electrons to higher states. They released photons upon returning to ground states, providing efficient, long-lasting illumination for sign displays and energy saving bulbs, leveraging their inertness to prevent filaments burnout. How does the size of a lanthanide ion change across the series? Lanthanide ion exhibit the lanthanide contraction where the ionic radius decreases from Ce 3 plus 1.034 angstrom to Lu3 plus 0.848 angstrom across the series. These results from the pore shielding of 4 electrons, allowing the increasing nuclear charge. Increasing the nuclear charge Z is equal to 58 to 71 to pull electron closer, reducing ionic size. This effect impact chemical similarity, separation difficulty, and application like smaller Lu 3 plus in phosphorus versus larger Ce 3 plus in catalyzed. What is a ligand in coordination chemistry? A ligand is a molecule or ion with one or more lone pair of electrons that can donate to a metal ion, forming a coordinate covalent bond. Example include monodentate ligands like NS3 via N, or chlorine, or polydentate ligands like ethyl diamine En, bidentate or EDTA hexadenate ligands determine the complex geometry, stability via solution, and reactivity, playing key roles in bioinorganic systems. Example H2O in hemoglobin and industrial catalysis. What is the primary source of tin? The primary source of cassiterite SnO2, a mineral mined in countries like China and industry and Indonesia. The extraction process involves crushing and roasting cassiterating to remove impurities, followed by reduction with carbon in a laboratory furnace at 1200 to 1300 degrees Celsius, producing a molten tin. This tin is refined by pulling or electrolysis, yielding a metal used in shoulder SnPb tin. plate, steel coating, and bronzy alloys. How do halogen reacts with alkali metals? Halogen reacts exothermically with alkali metals to form ionic halides due to electron transfer from the metal valence electrons to the halogen vacant orbit. Halogen vacant orbitals, for example, 2Na solid plus Cl ratio is equal to 2NaCl solid produce sodium chloride with sodium donating its 3s1 electron to chlorines 3p5 forming sodium plus and chlorine minus. Reactivity decreases around the halogen group Fe2 uh, uh, more more than iodine due to stronger XX bonds, but all reactions are vigorous, often with flame or explosion under heat.